Okay, I'm very glad to have Ljudmila Kamenova here from Stony Brook to talk about Kobayashi and algebraic non-hyperbolicity of hyperkaehler manifolds.
Thank you so much for the invitation. It is a pleasure being here at such a special place. So today we'll talk a little bit about non-hyperbolicity, a little bit of different flavor than what we're used to having here. We'll explore both Kobayashi and algebraic non-hyperbolicity of hyperkaehler manifolds. So first let me define what is a hyperkaehler manifold, or in other words, irreducible holomorphic symplectic manifold. This is a compact complex scalar manifold which is simply connected, and you have a global non-degenerate true zero form. The fact that it's non-degenerate, it means it induces an automorphism between the holomorphic tangent and cotangent bundle. And this implies that the canonical sheaf is trivial. In particular, you have vanishing first-chain class. And from the Bogomolov decomposition theorem, irreducible holomorphic symplectic manifolds are building blocks of compact Keller manifolds with vanishing version class, because up to some finite unramified cover, they decompose as Calabi-Yaus, products of Calabi-Yaus and hyperkahlers and chloride. In the simplest examples of hyperkaehler manifolds, you have K3 surfaces. And indeed, you can check that all of the conditions of the definitions are satisfied. It's scalar, simply connected, and you have a holomorphic non-degenerate form in H20. So in high-dimensional geometry, we don't have too many more examples. We have examples coming from Hilbert schemes of endpoints on K3 surfaces. This is a compact hyperkaehler manifold. Or you can do something similar to construct a generalized Kummer variety. Instead of taking a K3 surface, you just take an abelian surface. If you just take cube n of the abelian surface, it will have too many holomorphic two-zero forms, and it wouldn't be simply connected. But to resolve this, you can just take the summation map from the symmetric n plus 1 product of A to A, and then take the fiber over 0 of A. In this way, you get a hyperkaehler, which is simply connected, and it has one global 2-0 form.
Yeah, someone said that it was too low.
Oh, okay.
Recording in progress.
Okay, much better. Thank you. Okay, so in every possible complex dimension, now we have two examples of hyperkahlers. You have the Hilbert schemes of points on a K3 surface, and we have these generalized Kummer varieties, which are fibers of the composite map between. So you have the Hilbert automorphism, because the Hilbert scheme resolves these singularities of the symmetric product, and then furthermore you have this summation map to the abelian surface A, and then you take a fiber over a distinguished point, let's call it a 0 point, and that's how you get generalized Kummer varieties. And other than these classical examples, you also have two exceptional examples in complex dimensions 6 and 10, which come from moduli spaces of semi-stable shapes, either on K3 surfaces or abelian surfaces. So in the compact case, so far these are all of the examples we know. And each one of these examples is the formation equivalent to a Lagrangian fibration. So just like the case of K3 surfaces, you want to study some K3s that are simple to describe and possibly are dense in the moduli spaces. For K3 surfaces, such classes are Kummer K3 surfaces, quartics, and elliptic K3 surfaces. So in higher dimensions, we want to generalize the structure of elliptic K3 surfaces. And let's define what is the Lagrangian fibration. Lagrangian fibration on a plane-dimensional hyperkahler manifold is the structure of a fibration over the base CPN, whose generic smooth fiber is a Lagrangian abelian variety of dimension n. And one might say, well, this is a very restrictive structure. Why can't we expand the definition and have a smaller dimensional base or a larger dimensional base? Well, this is because of a theorem of Matsushita, which says that any possible fibration looks like that. So let's consider any fibration from a hyperkahler manifold to a lower dimensional base. Then, by Matsushita's theorem, the base is forced to have exactly half the dimension of m, and the general fiber is indeed a smooth Lagrangian abelian variety. And moreover, Huang proved that if the base is smooth, then indeed the base is CPN. Okay, so if you have any fibration structure on a hyperkahler, that's how it looks like. So then, just like on K3 surfaces, you have the intersection product. Bugomolov and Fujiki introduced this special intersection form on the second integral cohomology. And it behaves like the intersection product on K3 surfaces. Namely, it has signature 3 and then the leftover B2 minus 3. And it satisfies the Fujiki's relation, which is the top intersection of a class alpha is some positive constant C times this Bugomolov-Fujiki form Q of alpha to the n. And this is a very special relation which generalizes the intersection pairing on K3 surfaces. And the constant C only depends on the topological type of the hyperkahler. So in particular, if you have a fibration, let's say you take an ample class on the base. So assume the base is smooth, so it's CPN. Let's just take a hyperplane class on the base, pull it back to M. And then what you get is a net divisor. And because of this relation, since the pullback will come from the base, which is lower dimensional, the top intersection will be 0, which will be equal to some positive constant times Q of alpha to the n. So every time you have a fibration, you have this special class, which is the pullback of an ample class on the base, which will have a vanishing self-intersection with respect to the Bugomolov-Fujiki form. So that's on the next slide. So this is a simple observation. Indeed, if you have a fibration and take an ample class on the base, the pullback is met with vanishing Bugomolov form. And then it's conjectured, this is called the SYZ conjecture in the hyperkahler case, that if you have any net-like bundle on a hyperkahler, with vanishing self-intersection with respect to the movable form. Then it induces a Lagrangian fibration. So it's if and only if. This conjecture is true for all of the known examples of hyperkaehler manifolds. So it's known for the formations of Hilbert schemes, the formations of the generalized tumors, and also for O'Grady's examples. It's not known in general, but for the known examples, it is indeed correct. Okay, well, here you guys know about hyperbolicity and the Kobayashi pseudometric, but let me just go through the slides. So we know the Kobayashi pseudometric is the maximal pseudodistance such that any holomorphic map from the unit disk with the Poincare metric to this manifold or space M with the Kobayashi pseudometric is distance decreasing. And manifold is called Kobayashi hyperbolic when this distance is indeed metric. It's not just a pseudometric. And we were just talking about Brody. His Brody's theorem that you can characterize when M is Kobayashi hyperbolic, it is compact. It is compact. Kobayashi hyperbolicity is equivalent to non-existence of entire curves. But because today we'll talk about non-hyperbolicity, I reformulated it. If N is Kobayashi non-hyperbolic, then this is equivalent to saying that there exists an entire curve from C to M. And Kobayashi has these conjectures formulated it from the 70s that for K3 surface we have vanishing of the Kobayashi pseudodistance, and he formulated it for Calabi-Yau, but today we'll talk about hyperkahlers. So for hyperkahlers we have the same, and in particular weaker version of the second conjecture is that the hyperkaehler manifold is Kobayashi non-hyperbolic. So, of course, if the second point is true, then the third one follows. And here is some history behind the proof of these conjectures. So, the first conjecture was first established by Mukai and Mori in the early 80s. Because for projective K3 surfaces, you have families of elliptic curves covering them going in different directions. So then you can measure the Kobayashi pseudo distance between any 2 points. Basically, you take an elliptic curve going in one direction, then from the other point you get elliptic curve going to another direction. And then using the triangle inequality, you get the Kobayashi pseudo distance between them vanishes. So then there was a gap between the progress made, and in 2012, Misha Verbitsky and I proved that every known hyperkaehler manifold is Kobayashi non-hyperbolic. That's because we were interested in a different problem. We were actually trying to prove a density of Lagrangian fibrations in the moduli space of hyperkahlers. And because we proved density of Lagrangian fibrations, and once you have a Lagrangian fibration, you have all these abelian varieties as fibers, then you get non-hyperbolicity automatically. And another very nice result by Brody is that non-hyperbolicity is preserved in the limit. So if you have a limit of non-hyperbolic manifolds, it is non-hyperbolic. The same is not true for hyperbolicity. So if you take a limit of hyperbolic manifolds, it may or may not be hyperbolic. but for non-hyperbolicity, it is true. So then, because Lagrangian fibrations are dense in the moduli space of hyperkahler manifolds, it means that you can take any hyperkahler and analytically get it as the limit of Lagrangian fibrations in the moduli space. And therefore, once you have a Lagrangian fibration and you have density result, you have non-hyperbolicity of hyperkahler manifolds. Because for the non-hyperkahler manifolds, we know their Lagrangian fibrations. Otherwise, our theorem said that the Lagrangian fibrations in the moduli space are either dense or empty. And then, using the ergodicity results, Misha Verbitsky extended our results to all hyperkahler manifolds. And using the same hyperbolicity results, together with him and Stephen Lehn, we were able to further the results. We were able to prove this for K3 surface, the Kobayashi pseudometric vanishes. And for hyperkahler manifolds, or their singular version, called primitive symplectic varieties, with Picard rank less than maximum, and the formation equivalent for Lagrangian fibration, you also have vanishing. Initially, together with Misha Verbitsky and Stephen Lehn, we proved it in the smooth case. We proved it for a hyperkahler manifold. But later, Christian Lehn and I extended it to the singular case. There are various ways to see what kind of singular hyperkahler manifolds you have. We did it for primitive symplectic varieties, which I will define a little bit later. So this takes care of the Picard rank case, which is less than maximal, because here we can use ergodic methods. So then what happens if the Picard rank is maximal? Well, you have to make some extra assumptions. You have to first assume that the second data number is greater or equal than 7, and that the SYZ conjecture holds for all the formations of N. Then you also have vanishing of the Kobayashi pseudometric. Okay, and before I go with the proofs, let me also define a different notion of hyperbolicity, which was done by Demery. Let's have, for example, compact, complex, projective Kobayashi hyperbolic manifold. And so the property that's described here is called algebraic hyperbolicity. Basically, if you fix an ample class, you want the degree of the curve of any curve, or rather any non-constant holomorphic map from a smooth curve to n. So this will have degree which is bounded by above by 2g minus 2 up to a positive constant. So this is called algebraic hyperbolicity. So this means that Kobayashi hyperbolicity implies algebraic hyperbolicity. Together with Ariane, Javan, Picard, we generalized this notion of algebraic hyperbolicity. I didn't put it in the slides because we'll just be proving non-hyperbolicity of hyperkahler manifolds. But we also generalized it for not necessarily smooth projective schemes. So, then we have that Kobayashi hyperbolicity implies algebraic hyperbolicity. But because of the conjectures we have, Green-Griffiths, the Lehn conjecture, and the Mace conjecture, we have conjecturally the opposite is also true. That conjecturally algebraic hyperbolicity should also imply Kobayashi hyperbolicity. We don't know it yet, but conjecturally that should be true. Okay, so then in terms of non-hyperbolicity, once you reverse the directions, we have that algebraic non-hyperbolicity implies Kobayashi non-hyperbolicity. So then a further question to ask is, because we're proving non-hyperbolicity of hyperkahlers, are hyperkaehler varieties also algebraically non-hyperbolic? Okay, and together with Verbitsky, we prove this if you assume that the Picard rank is strictly bigger than 2, or if it's 2, you have that we need the SYZ conjecture. And then this hyperkaehler manifold is algebraically non-hyperbolic. So our proof relies heavily on the fact that if you have infinite automorphism group, then this implies algebraic non-hyperbolicity. And at first, Misha Verbitsky and I proved it for hyperkaehler manifolds specifically. But then Fabio Bogomolov, he saw our proof and he said, well, you guys can do it in general as well. You don't have to assume that N is hyperkaehler. So together with Bogomolov and Verbitsky, we proved that algebraically hyperbolic manifolds have finite automorphism groups, and therefore, if you have infinite automorphism group, then it's algebraically non-hyperbolic. And actually, a few years later, together with Ariane Picard, we generalized this to our new definition for projective schemes. But here we won't need it. Okay, so now what are some of the ideas of the proof? Well, first we'll be working with the Picard space, which is a moduli space of complex structures. So instead of working with moduli space of marked hyperkahlers, we'll just be working with the classical Picard space, because the Corelli theorem we have for hyperkahlers is on the Picard space. For a while, people were trying to do Corelli for marked hyperkaehler moduli spaces. However, it works better for the Picard space. For K3 surfaces, it's equivalent, but for higher dimensional geometry, for higher dimensional hyperkahlers, it's true for the Picard space. So the Picard space is just the space of complex structures, modulo connected components of the diffeomorphism group, and it admits a standard action by the mapping class group. We have that for Calabi-Yau or hyperkahlers, this Picard space is finite dimensional, and an element which is a complex structure in a Picard space, so you get a class, equivalence class of complex structures. It is called ergodic. If its orbit with respect to the mapping class group is dense in the Picard space. And Verbitsky classified when an action is ergodic. There is a period map from the Picard space to the period domain, which looks like a Grassmannian. And then in this Grassmannian, you have the corresponding points are positively oriented to planes. And Verbitsky proved that the action is ergodic if and only if the corresponding positive oriented plane contains no rational vectors. So that's the general case. So using global theory for hyperkahler manifolds, first what you can do with a Teichmüller space is do Hausdorff reduction. Initially, the Teichmüller space is rather non-Hausdorff, but the non-Hausdorff points correspond to birational hyperkahlers. And because of this, you can identify non-Hausdorff points. And this is an equivalence relation because for hyperkahlers, non-Hausdorff points or non-separated points correspond to birational hyperkahlers. So this becomes equivalence relation. And once you identify various birational hyperkahlers, you take this new moduli space of complex structures called Teichmüller B because birational identification. And then any connected component is identified with the period domain, which is a quotient of these non-compact Lie groups. And the action of the mapping class group descends on as an action on this period domain. And it turns out that this action is ergodic in the usual ergodicity sense. Using the measure, which is the Haar measure on the period domain, because you have a quotient of Lie groups. And what it means for an action to be ergodic, this means that if you have any measurable subset in this period domain, which is the gamma invariant, its measure is either 0 or the complement of it has measure 0. So that's what it means to be ergodic, like in dynamics. Okay, so some of our theorems are based on the following key proposition, which is a very simple proposition, but it's very important. So if you have a complex manifold with vanishing Kobayashi pseudodistance for some complex structure J, and then you have another complex structure I, which is the formation equivalent to J. If I is ergodic, then its Kobayashi pseudodistance also vanishes. So every time you have some ergodic complex structure with the same deformation type with some complex structure that has vanishing Kobayashi pseudodistance, the ergodic one also has vanishing Kobayashi pseudodistance. And the proof is based on a fact that's seen in some of Sue's papers, that if you take the diameter, which is a function from the Teichmüller space to R non-negative, then this function is upper semi-continuous. So, but then because it's upper semi-continuous and I is ergodic, what happens is the orbit of I is dense, and then in the limit points, the diameter can only jump up. That's the part of the upper semi-continuity. But because for this J, we assume that the Kobayashi pseudodistance vanishes, the diameter is 0. And because the diameter is always non-negative, it must be 0 for I as well. And this is the property of the Kobayashi pseudometric for compact complex manifolds. This is upper semi-continuous. Okay, so it's a very simple proposition, but it is useful. So then, using this proposition, let's prove that for any K3 surface, the Kobayashi pseudo-distance vanishes. So let's first take the maximal Picard rank. If K3 surface has maximal Picard rank, then it is automatically projective. And for projective K3 surfaces, you have vanishing of the Kobayashi pseudo-distance because of Mori and Mukai. You can cover them by rational or elliptic curves going in various directions. So then, if the Picard rank is less than maximal, then this is the case where either you have ergodicity or you have some intermediate case which behaves like the ergodic case. But in either case, you can always deform your K3 surface to a projective K3 surface since they're all deformation equivalent. And because of this proposition that we had, if you have some deformation with vanishing Kobayashi pseudo-distance, then the initial metric that you started with also has vanishing of the Kobayashi pseudo-distance. So that's how we prove the first theorem. Then, when we talk about hyperkahlers, we need something different. So in the high-dimensional case, we also need this key theorem. This is a special observation. What happens if you have two Lagrangian fibrations? And this is the same idea as the idea of projective K3 surfaces. If you have either a hyperkahler manifold or in the singular case a primitive symplectic variety, admitting two distinct Lagrangian fibrations, the way we say this technically is to be associated to non-proportional metaparabolic classes. So when you pull back these ample classes from the base, you want the pullbacks to be non-proportional. That's how you make sure that the Lagrangian fibrations are distinct. Then you have vanishing of the Kobayashi pseudo-distance. So the proof is the same as the case for projective K3s. You basically want two Lagrangian fibrations whose fibers intersect, so that then we can do the triangle inequality and get vanishing. So that's the key. You have to prove that the fibers intersect. So if you take ample classes HI on the two bases of the Lagrangian fibrations, and then pull back to classes alpha I, then the computation about intersections of fibers is just using the generalized Fujiki formula. So the intersection of these two fibers is just a positive constant times the intersection of the two classes alpha 1, alpha 2 to the n. Actually, that's positive. I wrote different than 0, but it is positive. You don't want one of them to be a component of the other. So, because it is actually positive, it means that the general fiber of one vibration intersects the general fiber of the other vibration. And therefore, we are able to connect arbitrary pairs of points using the two different vibration structures. And again, by the triangle inequality, you get vanishing. Okay, so this theorem was for having two Lagrangian fibrations. But what if you just have one? We have a hyperkaehler manifold with Picard rank less than maximum, which is the formation equivalent to a Lagrangian vibration. Then you have vanishing of the Kobayashi pseudodistant. And the idea is to take the locus of Lagrangian vibrations in the moduli spaces of complex structures, the Poincare space. So the locus of Lagrangian vibrations actually self-intersects, and then you take a general point in this self-intersection. It will have at least two Lagrangian vibrations, and then for this point you have vanishing of the Kobayashi pseudodistance. But because we're in the case where the Picard rank is less than maximum, and here you also have ergodicity, what you can do is deform this complex structure, the initial complex structure, to the complex structure with the vanishing Kobayashi pseudodistance, and then use this special proposition with the upper semi-continuity to finish the proof. Okay, so the idea behind the theorem 2 was to use both double Lagrangian vibrations where they intersect, and this proposition that because of upper semi-continuity of the diameter, you can deform, once you can deform something to a vanishing Kobayashi pseudodistance, the initial one was also vanishing. Okay, and then for the third theorem, what you have is the following. We have to assume that the SYZ conjecture holds because of the following. Well, if the second Betty number is at least 7, this means that the Picard number of the hyperkaehler manifold is at least 5. And then there is this theorem about lattices. If you have an indefinite lattice of rank at least 5, it has a vector, it has an element with vanishing self-intersection with respect to your form. In our case, it's the Bouvier-Bogomolov projective form. So there exists non-trivial parabolic class Z. So Q of Z vanishes, and then by the SYZ conjecture, it says that Z gives rise to a Lagrangian vibration. So then you have to do a bunch of work, but the idea is that by applying automorphisms, you get a second Lagrangian vibration, and then you can use the theorem for double Lagrangian vibrations. Okay, and maybe I'll mention just a few words about the singular setting. So these proofs work in the smooth case. In the singular setting, what is the singular hyperkaehler or primitive symplectic variety? This is a compact Keller variety, which is normal with rational singularities. Again, you want H1 of the structure sheaf to vanish and to have a unique symplectic form up to a scalar. So, and instead of the regular SYZ conjecture for the singular case, we use the rational SYZ conjecture. So if you have a primitive symplectic variety, which will be our version of hyperkaehler with singularities, if you have a non-trivial movable line bundle with vanishing Bouvier-Bogomolov form, then it induces a rational Lagrangian vibration. So you have a meromorphic map to a normal Keller variety with connected fibers, and whose general fiber is the Lagrangian subvariety of X. Okay, so that's the SYZ conjecture we use in the singular case. And together with Christian Lehn, we proved the version of our theorems in the singular case. So first, we want to assume that the rational SYZ conjecture is always satisfied. Then, if we assume that the second Betti number is a case 5, then we just get non-hyperbolicity. But if the second Betti number is the case 7, then we actually have vanishing of the Kobayashi pseudometric. And so, in the singular setting, we have to come up with some new ideas. So again, the first one is automatic from the rational Lagrangian fibration conjecture, the rational SYZ conjecture, because again, as soon as you have this bound on the second Betti number, you can apply Meyer's theorem on lattices and get a non-trivial vector with vanishing with vanishing Bouvier-Bogomolov Fujiki form, and then it gives you rise to a rational Lagrangian fibration.
Are there counterexamples that you need these inequalities as a theorem?
So far we have no counterexamples, but for the smooth case, all of the Betti numbers are at least 7. So for the smooth case, it will be interesting question to prove that the second Betti number cannot be 3, 4, 5, or 6. It's always 7 or up. But in the singular cases, we have small Betti numbers. You can hook up some singular examples with smaller Betti numbers. But even for them, we don't know, for the examples we have, we do not have counterexamples to this theorem. So it possibly this condition is just cosmetic because it's easier to prove it, assuming these conditions, but we don't know yet.
And the rational SYZ conjecture, is that been proved for some cases? Or just,
it's proved only in the smooth case, as far as I know. But that's a good question to ask somebody to prove it. That's a good PhD problem. So then, and then for vanishing of the Kobayashi pseudodistance, where our idea is also to find the two transversal Lagrangian fibrations. And that's why we need more room to move in the Ron-Severi lattice, and that's why we need this assumption for technical reasons, that the second Betti number is at least 7. And so together with Christian Lehn, if we start with one given Lagrangian fibration, we prove that there are two cases. Either this leads to a second rational Lagrangian fibration, which is transversal to the first one, and then we can proceed as in the smooth case. Or there is a second scenario in which instead of having a second rational fibration, you get some birational model like you get some non-trivial divisorial contraction, and then the contracted vibration is chain connected by fibers, and again you use the triangle inequality. So that's the difference between the smooth and the singular case. And I have some time to prove the algebraic non-hyperbolicity theorem. So this one has completely different methods. Okay, remember we're proving that now a hyperkahler manifold in the smooth case is algebraically non-hyperbolic if rho, which is the Picard rank, is bigger than 2, or if it's 2, we need the SYZ conjecture to hold. And of course, we suspect it's true also for Picard rank 1, but we don't know how to prove it. Okay, let's consider first Picard rank greater than 2, because we don't have to make additional assumptions here. And we'll have two cases. Either the Kahler cone coincides with a positive cone, which is the general case, or if it's strictly less. Okay, so if the Kahler cone coincides with a positive cone, then one can prove that since we also have that the automorphism group of the hyperkahler is commensurable with the group of isometries on the integral lattice H2 with integral coefficients, preserving the Hodge decomposition. So preserving the same Hodge type, which because H20 is one-dimensional and H02 is the conjugate of that, well, you have type 1, B2 minus 2, 1. So using Borel and Harshchandra's theorem, any arithmetic subgroup of SO1 rho minus 1 is lattice if rho is bigger than 2. And then by Borel's density, we see that since any lattice in a non-compact simple E group is Lagrangian dense, then we have this group of isometries of H11 is infinite. But because the automorphism group is commensurable with it, so up to finite, up to some finiteness is the same, we can apply our theorem with Bogomolov and Verbitsky, saying that once you have infinite automorphism group, then you have algebraic non-hyperbolicity. And this took care of the case where the Kahler cone coincides with the positive cone. And the other case is simpler. So if the Kahler cone doesn't coincide with the positive cone, what it means is the positive cone breaks into chambers, just like for the K3 surface. It's broken into Kahler chamber, like a Kahler chamber, and then translations of this Kahler chamber. And the walls of this subdivision are determined by various rational curves. Basically, these walls are perpendicular with respect to the Bouvier-Bogomolov projective form to some curve classes. But this means rational curves exist on M, and then it's automatically algebraically non-hyperbolic. Okay, so always when the Kahler cone doesn't coincide with the positive cone, we automatically have algebraic non-hyperbolicity. And that's true also in the case when rho is 2. And of course, when rho is 1 as well. But then, now let's assume that rho is equal to 2. So you have Picard rank 2. We can no longer apply Harshchandra's theorem, so we have to do something else. Well, one can do some lattice theory. And if you assume that, now let's assume that the positive cone and the Kahler cone coincide, and you have Picard rank 2. And let's take two cases. Either there is a class which is parabolic and non-trivial, Or there is, and then we can apply the SYZ conjecture by getting a rational vibration and then getting rational curves. Or if it's, or if such class doesn't exist. But one can play with lattice theory a little bit and see that if you have a lattice with this property, that there is no non-trivial parabolic class, then this lattice is actually isomorphic to this precise lattice, p times v2. So, but the good thing about this is that it's infinite. So, and therefore, again, the automorphism group, which is commensurable to this one, must be also infinite. And we can apply our theorem with Bogomolov and Misha Verbitsky and deduce algebraic non-hyperbolicity as well. And of course, when the case when you have rational vibration, that's ultimate. Okay, well, these are all the theorems I wanted to present, and special thanks for the organizers, and it's a pleasure being in such a nice place in Miami.
Thank you.